What if I told you that one physics practical experiment can test for Hooke's law, simple harmonic motion, graph interpretation, calculations, and experimental skill all at once? Yet many candidates lose marks because they don't understand the relationship between extension, oscillation, and spring constants. In this video lesson, I will show you how to carry out this practical like an examiner expects. If you're preparing for JUPEB, IJMB, or any advanced level physics practical, this is a lesson you cannot afford to miss. So grab your notes, let's master this practical together. If you are just joining us, do well to like this video, share it with your classmates, and subscribe to Organotope Science Academy. Trust me, I will take you through this practical procedure step by step so that you can conduct the practical independently in your exams. We are to suspend the spiral spring vertically from the retort stand. Then attach an optical pin at the lower end of the spring, which acts as a pointer. Then we clamp the meter rule beside the spring and we adjust until the pointer moves freely. Moving on, can we attach only the mass angle and record the initial reading L0 from the meter rule? For this experiment, I'm using a 20-gram mass angle. Let's record the initial reading L0. So we have from the meter rule 11.10. So can you see that we have 11.10 for L0? So let's record the value of L0. We have 11.10 centimeter. Okay, so we are going to convert to meter, which is the standard unit of measurements. For experiment 1, can we add a mass of 20 grams to the 20-gram mass angle, making a total of what? 40-gram mass. And we allow the spring to come to rest. Now let's record the value of L for the first experiment. From the meter rule, we have 16.20 for the value of L in experiment 1. Look at that, we have 16.20. We have 16.20 centimeter. We are expected to record our value in meter. So the standard unit of measurement is meter, okay? How do we convert centimeter to meter? We do what? By dividing by 100. So we need to divide by 100 to get our value in meter. So we have 16.20 divided by 100 will give 0.162. Okay? Can we also convert the L0 to meter? We divide by 100. So we have 0.111 meter. Okay? So we've been able to convert to meter. In order to determine the value of extension, we subtract L0 from L for each experiment. So when we subtract 0.111 from 0.162, we have 0.05. Okay? So that is the extension for experiment 1. Make sense? Now let's determine the time for 20 complete oscillation for the 40-gram mass. Then we are going to pull the mass slightly downward at an amplitude of 2 cm and release gently in order for it to perform vertical oscillation. Let's measure time T for 20 complete oscillation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So for the first experiment, I have the time T for 20 complete oscillation as 13.34. So that's the time taken for 20 complete oscillation when 40-gram mass is hung on the spring. So can we record that on our table? We have 13.34. Okay, so that is the time taken for 20 complete oscillation when we have 40-gram mass hung on the spiral spring. We are going to repeat the same procedure when 30-gram mass, 40-gram, 50-gram, 60-gram, and 70-gram mass is added to the mass angle. So when 30-gram mass is added to our 20-gram mass angle, we have 50 gram. And when 40-gram mass is added to our 20-gram mass angle, we have 60 gram. When 50 gram is added to our 20-gram mass angle, we have 70 gram. When 60 gram is added to the 20-gram mass angle, we have 80 gram. And when 70 gram is added to the 20-gram mass angle, we have 90 grams. So we are going to conduct the same procedure for experiments 2, 3, 4, 5, and 6. Make sense? In order to save time in an exam condition, take all the values of L from experiment 2 to experiment 6, okay? So we are going to do that now. We are going to take all the values of L. So for experiment 2, I have a total mass of 50 grams, okay? So I have 50 gram mass. Can I determine the value of L? So the value of L for experiment 2 is 18.40. So we have 18.40. So can I record the value of L? We have 0.184, okay? When we divide 18.40 by 100, we have 0.184 for experiment 2. Now, can we remove the 50 gram mass? Then I'm going to introduce 60 gram mass for the next experiment 3. Can I determine the value of L when 60 gram mass is attached to the spring? We have 21.10. So 21.10 is equivalent to 0.211, okay? So that's after converting to meter. We have 21.10. Now, can we determine the value of L for experiment 4? So we remove the 60 gram mass and we introduce the 70 gram mass. For experiment 4, the value of L is 23.20, okay? So we have 23.20, which is the same thing as 0.232 when we divide by 100 to convert to meter. So right there we have 23.20 centimeter. For experiment 5, I'm going to remove the 70 gram mass and I will attach a total of 80 grams to the spring. Then we can determine the value of L. The value of L for experiment 5 when we have 80 gram mass is 25.90. So we have 25.90. When you divide by 100, we are going to have 0.259. So we have 25.90 centimeter for experiment 5. So can we remove the 80 gram mass? Then we attach 90 gram mass to the spiral spring. Then we take the value of L for the last experiment, which is experiment 6. Let's take the value of L for the 6th experiment. We have 28.00 centimeters. When we convert to meter, we are going to have 0.280. Make sense? So we have 28.0 centimeter for the last experiment. Now, can we record the values of extension E by subtracting L0 from L for each experiment? Since we've recorded the values of L for each experiment, now let's subtract 0.11 meter from the values of L. Now, can we subtract the value of L0, which is 0.111 meter, from each experiment? So we continue with experiment 2 since we have the value for experiment 1. So for experiment 2, we are going to have 0.073. That's the value for the extension. And for experiment 3, we have 0.100. Experiment 4, we have 0.121. Okay. And for experiment 5, we have 0.148. And the last experiment, which is experiment 6, we have 0.169. Okay, so the extension is determined by subtracting L0 from the values of L. Make sense? Now, can we determine the time taken for 20 complete oscillation for experiment 2 when the total mass is 50 grams? So we are going to hang the 50 gram mass in order to determine the time taken for 20 complete oscillation. So can we displace the mass at an amplitude of 2 centimeters to carry out the 20 oscillation? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So right here we have 14.84 when 50 gram mass is hung on the spiral spring. Can we record the time taken for 20 oscillation for experiment 2? We have 14.85. Okay. Moving on, can we determine the time taken for 20 oscillation when a 60-gram mass is hung on the spiral spring? So we have a 60-gram mass right here, and we are going to put it into oscillation by displacing it downward at an amplitude of 2 centimeters. So we displace slightly at an amplitude of 2 centimeters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the time taken for 20 oscillations when 60-gram mass is hung on the spiral spring is 16.15. So we have 16.15 right here. 16.15. So can we record the time taken for this oscillation? For experiment 3, we have 16.15. Now let's take the fourth experiment when we have a total of 70-gram mass on the spiral spring. So we have a 70-gram mass right here. So we are going to hang it on the spiral spring, and we put it into oscillation by displacing the mass vertically downward at an amplitude of 2 centimeters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So can we check the time taken for 20 oscillations when a 70-gram mass is hung on the spiral spring? We have 17.43. 17.43. So can we record the value for the time taken? So we have 17.43. 17.43. Let's consider experiment 5 when we have a total mass of 80 grams. So let's hang the 80-gram mass on the spiral spring, and we are going to displace it downward at an amplitude of 2 centimeters for a vertical oscillation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So for 20 complete oscillations, we have 18.72. Right here we have 18.72. So we record the value for the time t, 18.72. Okay, so that's the time taken for 20 oscillation when we have a total mass of 80 grams on the spiral spring. I hope you can see that this experiment is an interesting one and it is very easy to carry out. So we are going to take the last experiment, which is experiment 6, when we have a total mass of 90 grams on the spiral spring. So we have 90-gram mass right here. So I'm going to hang it on the spiral spring and displace it vertically downward. So we displace vertically downward to determine the time taken for 20 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. For the last experiment, the time taken for 20 oscillations is 19.62. We have 19.62. So we can record the time taken for that oscillation, 19.62. Makes sense? So we've been able to determine the time taken for 20 oscillations for each of the experiments. So can we move to the next column to determine the period of oscillation for each experiment? So how do we determine the period for each experiment? We are going to divide the time t by the number of oscillations. So what's the number of oscillations? That's right, 20 oscillations. So we divide each value of time t by 20 in order to determine the period of the oscillation. Can we record the values for the period of each experiment? So for experiment 1, we have 0.667. When we divide this time t, 13.34 by 20, we have 0.667. For the next experiment, we have 0.743. Experiment 3, we have 0.806. Experiment 4, 0.872. Experiment 5, 0.936. And the last experiment, which is experiment 6, we have 0.981. Make sense? Let's consider the last column, which is the t-square. So we are going to square each value of the period from experiment 1 to 6. So can we record the values of t-square for each experiment? So we are going to have 0.445. When we square this value right here for the period, we're going to have this value. T-square for experiment 2 is 0.552. For experiment 3, 0.650. Experiment 4, 0.760. Experiment 5, 0.876. And the experiment 6, the t-square value is 0.962. Makes sense? Can we deduce the possible plots that we can have for this experiment? For simple harmonic motion that involve a loaded spring, we have the expression for the period of oscillation as C equals 2 pi square root of E over G. Okay? So from this expression, can we square both sides of the equation? So we have T square equals 4 pi square dot E over G. Okay, so from this expression we have this G is a constant, so we can bring it together with the 4 pi square right here. So I have T square equals 4 pi square over G times what? E. Now can we linearize the expression using the equation of line graph? We have y equals mx plus what? Plus c. So from here, the y component is t square, the slope is 4 pi square over g, and the x component is the extension. The other possible plot that we can have is when we make the extension e the subject of the equation, so the expression becomes e equals g over 4 pi square times c square. So in this case, the y component is the extension e, and we have the slope is g over 4 pi square, and the x component is t square. So the intercept is equal to 0. When the intercept is equal to 0, it implies that the straight line will pass through the origin. So we have two cases for the plots of the graph for this experiment. So let's take this as case 1, and we have this as case 2. Okay, so the graphical representation for the case 1 is this. We have a y component and the x components. So what is the y component? We have t square. So on the y-axis we have t square, while on the x-axis we have extension e. Okay, so we're going to have a straight line passing through the origin right here, and we draw our right angle triangle in order to determine the slope of the graph. So the slope is 4 pi square over g. So we have 4 pi square over g for case 1. Okay, and the intercept is equal to 0. That is the reason why it is passing through the origin. Here is case 1. Okay, so for case 2 we have a similar graph passing through the origin, but this time around the component y is the extension e. So we have extension e, while the component x is the t square, the square of the period. So we have t square, right? So it will also pass through the origin. The straight line will pass through the origin. So can we take the slope? So the slope for case 2 is g over 4 pi square. So we have g over 4 pi square. Okay, so the line passes through the origin. So we have this as case 2. Okay, so what is the aim of this experiment? The aim of the experiment is to determine the acceleration due to gravity g by using the Hooke's law as well as the simple harmonic motion. So once the slope of the graph is known, then we can determine the value of the acceleration due to gravity from this expression. We are going to have S equals G over 4 pi square. I'll make G the subject of the equation. So we have G equals S times 4 pi squared. So this will be the value for the acceleration due to gravity. When you substitute the value of the slope gotten from the graph into this expression, you determine the acceleration due to gravity. Make sense? If this lesson helped you, like this video, share it with your classmates, and subscribe to Organotope Science Academy for more practical tutorials and exam-focused solutions. See you in the next practical class.